Hi everyone and welcome back to my channel in Economist. So this is going to be part 7 of classical linear regression model analysis where we will start with hypothesis testing. So particularly in this video I will show you how to conduct test for beta. Test for beta. Beta is the slope parameter. Beta is the slope parameter of our classical linear regression model, that is the two variable regression model, linear regression model. So I'll discuss in details how to conduct test for beta. I'll show you how to derive the confidence interval for beta. And in the later part of the video, we will solve questions on this and we will manually solve and make statistical inferences based on this, right? So let us straight jump into the concept. What is hypothesis testing? Here I have given you the brief outline of how you manually do the hypothesis testing. Here I will not use any softwares. I will make separate playlist for softwares. Here, whatever we will do manually, right? So hypothesis testing basics. I hope you guys know these things, but just to give you the entire thing, I have given you this. So let's start. What is hypothesis testing? Hypothesis testing is a statistical method that we use to make inferences. So it's a part of statistical inference about a population based on sample data, So suppose you have this two variable regression model, alpha plus beta x plus epsilon. So this is the simplest, most classical linear regression model. Now you want to know, you as a researcher or as an econometrician, you want to know, is your intercept parameter significant or not? Do we need to include this intercept parameter in our model or not? Does it, has any statistical significance, right? So if you want to test that, you will use hypothesis testing. Similarly, for the slope parameter beta, you want to know, do your x variable has any impact, statistically significant impact on your y variable or not, right? Dependent variable y or not. So in that case also, you will conduct hypothesis testing. And how do you do that? You have to follow the 7 steps in order to conduct hypothesis testing. So first step is to define a null hypothesis. Null hypothesis is written as H naught. H naught is the null hypothesis, and please remember this thing, that null hypothesis and alternative hypothesis is always defined on population parameter. Here we are not talking about any sample statistic, right? We are not talking about any sample statistic. Whenever you define any null hypothesis or alternative hypothesis, we want to make inference about population. See the definition? Inferences about a population parameter. Here there are two population parameters, alpha and beta. So we will work with alpha and beta only and based on sample data. So we will use sample data to test our parameters and to test that they are statistically significant or not. But the null hypothesis and the alternative hypothesis will be defined only on population parameters. So please be very clear about this. Okay. So what is null hypothesis? In null hypothesis, we assume that there is no effect or there is no difference. No difference between the variables. Here we will say if your either your beta is 0 or your alpha is 0, if this hypothesis is accepted or we fail to reject this hypothesis, then we say that there is no statistical significance of the intercept parameter and the slope parameter basically. So that is the null hypothesis. In null hypothesis, we assume that these population parameters are not statistically significant in our context basically. Now, the second one is alternative hypothesis, which is written as H1 or HA. Here, this statement contradicts H naught. This is just the polar opposite of H naught, suggesting an effect or a difference exists, or we will say that either beta is not equals to 0 or beta is greater equals to 0 or beta is less than 0, and similar thing will be done for alpha, and we will say that yes, these parameters, population parameters, are statistically significant and they are different from Z. So this is the alternative hypothesis. I'll write everything in a while. So just, take a look at the steps first. Third thing is to define a significance level. Significance means the level of type 1 error. What is type 1 error? The probability of rejecting H naught when it is true. So if it is so that your null hypothesis is true, but erroneously you have rejected the null hypothesis, then we say in statistical inference that you have committed a type 1 error. So in any kind of hypothesis testing, we make a room for errors. So we are basically humans, we make errors, right? We cannot be error free all the time. So in hypothesis testing, we make a room for error, and we say that yes, we will accept a level of significance that this much error is permissible. When we are conducting this hypothesis testing, some level of some percentage of error we are permitting, some percentage of type 1 error we are permitting, and that percentage is known as the level of significance, which is denoted as alpha in hypothesis testing. So the probability of rejecting H naught when it is true, typically we take this as 5%. So in any hypothesis testing, we generally assume that there is 5% room for error. The probability of committing type 1 error is 5%, right? Since we are doing it manually, there must be some error that we are committing, and we say that, okay, this 5% error we count into our analysis, right? So this is level of significance. Then the next step is to define the test statistic. What is test statistic? It's a value that is calculated from the sample data. Now that we want to test our population parameters based on sample, so the sample data comes in the form of test statistic. We will define our test statistic in terms of our sample data, and I'll show you how to do this. So it's a value calculated from the sample data to determine whether to reject or accept H naught, right? So this will help us in order to conduct the test. For example, T statistic and Z statistic. So if you have seen my previous videos, I have given you the background of T distribution and Z distribution. If you haven't watched that video, please check that out. I have made that video just because I plan to start hypothesis testing from this video, so that you find it easier. So take a look at that video first. Okay. Moving on, the next is the critical value or the p-value. Now, p-value, when we test hypothesis manually, we do not calculate p-value. P-value is given to you in the softwares automatically, right? When you perform this hypothesis testing, suppose you are doing it in Python or R or maybe Stata, in whichever platform you use this hypothesis testing, this p-value will be given to you in just one line of code, right? So, but manually when we do not usually calculate p-value. We use the test statistic in order to come to any decision making. So, but just for your understanding, I have given this, that it's the threshold or the probability used to compare against the test statistic to make a decision. Now, what is decision rule? Next thing is decision rule. If a test statistic falls in the rejection region, that is p-value less than alpha, we reject H naught. Otherwise, we fail to reject H naught. So this is basically the decision rule. And the seventh thing is defining a conclusion that based on the test results, we will conclude whether there is sufficient evidence to support H1 or not. So these are the 7 steps that we basically use in order to conduct our hypothesis testing. I hope this is absolutely clear. So please remember these 7 things. Okay. Now let us start with hypothesis testing in CLRM. So we know that CLRM model looks like this. Yi is alpha plus beta xi plus epsilon I. This is our CLRM model where I is going from 1 to up to n. So this is a simple 2-variable linear regression model. In 2-variable linear regression model, what we conduct is known as individual test. Individual tests. What are individual tests? So individual test means we want to say H naught. We define H naught. Suppose we are conducting test for beta, then we will define the null hypothesis as simply this. We will say null hypothesis is beta is 0, which means if you accept this null hypothesis, we are saying that beta has no significance, no statistical significance on our dependent variable, that is y in our particular case, right? Now versus what is the alternative hypothesis? You can define alternative in different ways. You can define it in this possible way. This is one way. This is also known as two-tailed test. Two-tailed test. So when you are saying that beta is not equals to 0, you are making the room for beta greater than 0 as well as beta less than 0. So we don't basically know what is beta. So it is two-tailed. But you can define it, or you can define it in this way also. H1 is beta greater than 0. Or you can define it in this following way. H1 is beta less than 0. These two tests are known as one-tailed test. One-tailed test, right? So these are the individual tests for the slope parameter beta. This is the slope parameter. Slope parameter. But you have an intercept parameter as well. So for intercept parameter, in the similar way, you can conduct your hypothesis. So what will you write? Here the H naught will be null hypothesis is alpha equals to 0 versus what will be the alternative? Alternative can be either alpha not equals to 0, again two-tailed test, or it could be, alternative could be alpha greater than 0, or it could be alpha less than 0, right? So these are the possibilities. This is how you conduct individual test. This is one-tailed test, right? This is how you define individual test not statistic, individual test, null hypothesis and alternative hypothesis. So individual test means you are considering only one population parameter at a time. See here, I have used only beta, here I have used only alpha. But this is the case only, this case will be valid only if it is a two variable regression model, right? It is a two variable regression model. But what if we extend our model like this? Yi is alpha plus beta x I plus gamma zi plus some ui. Suppose our model is like this. I is from say 1 to n. This is a multi-variable model, or more specifically three variable model, right? Three variable model, which we also known as MLRM model, multiple linear regression model. Not CLRM, this is MLRM. So in case of MLRM, you can conduct two types of tests. First is the individual test. First is the individual test that we have done for CLRM as well. So let me write what are the possible cases for here. Here the first case can be H naught alpha equals to 0 versus H1 can be alpha not equals to 0. Or the second test that you can conduct, beta equals to 0 versus H1 beta not equals to 0. Or the third thing that you can do, here you see alpha, beta and gamma is another extra parameter. So you can use that as well. Gamma equals to 0 and H1 is gamma not equals to 0. So these are two-tailed tests, and similarly you can define one-tailed tests as well. But here you have one additional test which is known as the joint significant test. Joint significance, joint significant test. So here what do you do? Here you define like this, H naught. You take two population parameter at the same time. Suppose I take this beta and this gamma at the same time, or you can do it alpha and gamma also, or you can do it alpha and beta also. So this is a joint significant when you take two population parameter at the same time. And the alternative is beta not equals to gamma not equals to 0. So in the similar way, you can define other things as well. Alpha equals to beta equals to 0. Alternative could be alpha not equals to beta not equals to 0. Right? So these tests can also be performed. So what I have done is that I have given you the distinction of hypothesis testing in CLRM and MLRM model. So in CLRM, since you have only two parameters, you can conduct only individual test and not joint test. But in case of MLRM model, you can conduct both the individual test and a joint test, right? Now, let us straight away move into test for beta in CLRM. So in this video, I will cover only the test for beta and we will solve questions on that. In the next successive videos, I will go into test of alpha and test for others as well. So let's see how to conduct test for beta. So first things first, you need to know the distribution beta cap. So please remember, we have derived the mean and the variance of beta cap. So what were they? We have showed that beta cap follows normal distribution with mean beta. And what was the variance? It was simply this. If you don't remember this thing, please check that out. I have derived this thing in details. I'll give the link of the playlist in the description. So please see this thing, how this is coming, right? So now what you have to do, you can standardize this thing. We have to know what is the distribution of the test statistic. For that, what we need to do, we need to standardize. Let's see, beta cap minus beta upon this sigma square upon Sxx. So this is what? This will follow a standard normal variable. I have covered this in details in the previous video, how to standardize and how to convert this into a standard normal variable. So what you have to do, simply from beta cap subtract this mean value and divide it by the standard error. So you will get a normal distribution. And also here sigma square is always unknown. Sigma square is always unknown. So basically we need to estimate this sigma square, and we have already seen what is sigma cap square. Sigma cap square also I have derived previously, RSS by n minus 2. And in the previous video, I have showed you that this sigma cap square follows the distribution, not sigma cap square, RSS. RSS upon sigma square follows the distribution chi square with n minus 2 degrees of freedom. So these are the things you need to remember. This thing I have derived just in the previous video. You can check that out. This also I have derived in the previous video. So refer to that. So these things we know. Also, another thing that I have told you is that how to define a t variable. How to define a t variable? T variable is on the numerator you have standard normal, and in the denominator you have chi square upon the appropriate degrees of freedom. This is the relationship between t variable, standard normal and chi square. This also, if you remember, I have covered this. So this is the thing. Now, how to write this particular thing, this and this. See, here you have the standard normal variable, here you have the chi square with appropriate degrees of freedom. So what we can do, we can divide and convert everything into a t distribution. So let's see how we will do this. So in the numerator, write the standard normal thing, sigma squared upon Sxx. In the denominator, write the chi squared variable. Chi square is RSS upon sigma square. And then divided by appropriate degrees of freedom. Here appropriate degrees of freedom is C n minus 2. Once you do that, you can cancel out certain things. This sigma square and sigma square is gone. Now this particular thing, this entire thing now follows T distribution with n minus 2 degrees of freedom. The degrees of freedom that you have for chi square and the degrees of freedom of the T distribution will always be the same. I have mentioned this in the previous class, right? So previous class was very crucial in order to understand this lecture. That is why I am giving very much emphasis to that class, right? So this much is fine. Now what you can do, you can simplify beta cap minus beta upon root over of sigma square, not sigma square, sorry. This is RSS, and then you have n minus 2, and then you have Sxx. So this follows Tn minus 2, or you can write beta cap minus beta upon. Now can you identify what is this value? RSS by n minus 2? Yes, RSS by n minus 2 is sigma cap square upon Sxx and root over of that. So this thing follows n minus 2. So this will be the distribution of our test statistic. This will be the distribution of our test statistic, where see, where standard error of beta cap is nothing but root over of sigma cap square by Sxx, and variance of beta cap is nothing but sigma cap square by Sxx. Right? I hope up till this much, this is absolutely clear to you. Okay, now let us define the test statistic formally. So this is basically the distribution of the test statistic. So let us define the test statistic. Now, to test H naught beta equals to 0, we use the test statistic. Which is given as this T beta cap upon standard error of beta cap under H naught, which follows T distribution with n minus 2 degrees of freedom. So I hope this step is clear to you. If you have any doubt anywhere, you can let me know. So this is the distribution, this is the test statistic. See, beta cap minus beta upon the standard error of beta. Now under H naught, beta is 0. Under H naught, beta is 0. So you can simply replace this to be 0. So you will get beta cap upon the standard error of beta cap, which will follow T minus 2 degrees of freedom. This is the test statistic, right? So let us move to the next step where we will derive the confidence interval now. So the test statistic portion and defining. So let's see the steps. So we have seen how to define the null hypothesis and how to define the alternative hypothesis. Level of significance is always, we will consider it to be 5% unless it is mentioned anything different from this. And we have derived the test statistic. So test statistic follows T distribution in our particular case with n minus 2 degrees of freedom. Now, what do you have to do? You have to define the decision rule and the critical values. For that, you need something called the confidence interval. In order to define the critical values, you need something called the confidence interval. So let's see how to derive the confidence interval now. What is confidence interval? It is a range of value derived from the sample data that is likely to contain the true population parameter with a specified probability, that is the confidence level. For example, a 95% confidence interval means that if we were to take many samples, 95% of the calculated intervals would contain the true population parameter. So this is the definition of confidence interval. Basically, if you see this diagram, this is a T distribution. If you remember, this is a T distribution which is symmetric about 0. So the mean is 0. The mean of a T distribution is 0. Suppose, let us consider this is a T distribution and we are conducting a two-tailed test. So this particular thing will be the rejection region, and this particular thing will also be the rejection region. This pink shaded region is the rejection region where the total area of the rejection is alpha. So total area is alpha, that is the probability of type 2 error, which is divided into these two regions by alpha by 2 and alpha by 2. So equal probability. So see, here you have alpha by 2 probability, here you have alpha by 2 probability. If you add these two regions, you will get the total significance level. So your probability of committing error is this alpha. So suppose if your test statistic value falls, calculated test statistic value falls in this particular region, anywhere in the critical region, in the rejection region, or in this particular region, you will reject the null hypothesis, right? You are in the rejection region. These are called the rejection region, and here in this region is the confidence level or the confidence interval. This is the confidence interval. So if you consider it to be 95%, it basically means that as many times you take the sample. See this definition, 95% means as many times you take the sample, 95% of the times your true population parameter will fall in this region. You can take the sample as many times as you want. 95% times you will see that your true population parameter will fall from this region to this region. This region, right? I hope you can see this and it's clear to you. This is the confidence interval region. And the boundary points, this boundary points of this confidence interval is called the critical value. This critical value. So boundary of the confidence interval are the critical value. So in case of our analysis, we will define the critical value as this. Yours, this side, this critical value can be written as this T, then you have alpha by 2, and then you have degrees of freedom n minus 2. And here, what is the critical value? Minus T alpha by 2 n minus 2. So this is the formal way of writing these critical values, and these critical values will help us to, come to a decision. So to make the decision, to make the inferences based on this analysis, we have to use this critical values, right? So let us formally define the confidence interval now. Let us see how to derive this confidence interval. So we will basically derive this critical values. What will be the confidence interval? Boundary points. We'll define these boundary points. So confidence interval for beta. How do you write this? You write this in this way. To find 100, 1 minus alpha percent. So if you put alpha to be 0.05, you will get this to be 95%. See, it is another way of writing 95% confidence interval. Formally, you write it in this way. You can put the values of alpha and then see it will be 95 or 99, whatever you take this to be. Of beta, we have what you will write. You will write in this way the probability. This step is very crucial. Please see this step carefully. Probability t alpha by 2 n minus 2 less than equals to your test statistic, standard error of beta cap less than equals to t alpha by 2 n minus 2 is nothing but 1 minus alpha. So this thing will be clear from this picture. See, here you have total probability is what? Total probability is 1, right? Area under the curve, area under this entire t distribution is 1. Here you have probability alpha by 2 or area. Probability is nothing but area. So area of this region is alpha by 2, area of this region is alpha by 2. So alpha is gone. So what are the remaining probability? Remaining area is 1 minus alpha. So this confidence interval has the probability 1 minus alpha. That is what I have written in this particular thing. See. So your test statistic, the calculated value of your test statistic will lie between this critical region. Critical region is minus t alpha by 2 n minus 2 to t alpha by 2 n minus 2. So the probability of that should be in this region. So basically, your test statistic value will fall in this particular interval has the probability of 1 minus alpha, right? This is what I have written it mathematically. Now you can simplify. What you can do, probability minus t alpha by 2 n minus 2, and then you can multiply the standard error on both sides. Standard error of beta cap. So, and then minus beta cap less than equals to minus beta less than equals to t alpha by 2 n minus 2 into standard error of beta cap. Then you have minus beta cap. This will be 1 minus alpha, or probability beta cap plus t alpha by 2 n minus 2 into standard error of beta cap is greater equals to, so you are basically multiplying minus on all the sides, is greater than equals to beta cap minus t alpha by 2 n minus 2 into standard error of beta cap. Now if you write it in a good way, what will you get? The final confidence interval for beta will come out to be this. Beta cap minus t alpha by 2 n minus 2 into standard error of beta cap 2. This is comma beta cap plus t alpha by 2 n minus 2, and then you have standard error of beta cap. So this is the confidence interval of beta. So basically, the critical values, we have derived the critical values this side to this side. This is the confidence interval. This is the boundary points of the confidence intervals can be derived using this formula. So this is the lower class boundary. This is the lower class boundary, and this is the upper class boundary. Right? This is how you define the confidence interval for beta. Now, one final thing is left for us is to define the decision rule. Decision rule. So let's see. So we have done null hypothesis, alternative hypothesis, significance level, test statistic, critical values. Now the sixth point is to find out the decision rule. Let me write the decision rules for you. T is what we know, beta cap minus beta naught. Beta naught is beta under H naught, basically standard error of beta cap under H naught, which follows T distribution with n minus 2 degrees of freedom under H naught. Don't need to write here, I have written this. So let we want to test H naught beta equals to beta naught. Then there could be three possibilities. The first possibility is if the alternative is beta greater than beta naught. This is one possibility. Then we reject H naught. So this is something like this. T greater than T alpha n minus 2. The second possibility would be if H1 beta less than beta naught, then we reject H naught if, here also you will have a if T is less than minus T alpha n minus 2. And the third thing is if H1 beta naught equals to beta naught, then we reject H naught if T greater than T alpha by 2 n minus 2 or T less than minus T alpha by 2 T less than minus T alpha by 2 n minus 2, which basically implies that mod T is greater than T alpha by 2 n minus 2. So these are the three possible cases. Now let me show you this in a diagram. So first case, I'm drawing a freehand diagram just to let you understand things. So this is a T distribution and you are performing a right tail test. See, beta is greater than beta naught, so you will have only one rejection region on the right hand side. Suppose this is the rejection region. This is the rejection region and this side the probability is alpha. Now what I am saying is that this value is T alpha n minus 2. This value is T alpha n minus 2. Now what is the rejection rule? If T value, that is the calculated T value, is greater than this quantity. If your calculated T value lies anywhere in this particular region, then you will reject it, right? So this is a simple first case. Now the second case says this is a left-tailed test. So the rejection region will fall on the left-hand side. This is the rejection region. Now this is alpha and this value is minus T alpha n minus 2. Now what happens is that if your T calculated value falls less than this, so your calculated value falls in this particular region. This is the value minus T alpha n minus 2. So your value, if falls in this particular region, you will reject H naught. And the third case, which is like this. This is a two-tailed test. See? This was left-tailed test, this was right-tailed test, and this is a two-tailed test. You do not know that beta is greater than beta naught or less than beta naught. So beta is not equals to beta naught. So here you will have two rejection regions, one on this side and one on the other side. This is one rejection region which has the area this. This is another rejection region which has the area this. And what about these values? this particular value is T alpha by 2. Now this significance level is divided in 2, right? T alpha by 2 n minus 2, and here you will have minus T alpha by 2 n minus 2. So these are the three cases and these are the three critical regions. So if your values, calculated value fall in this particular region or in this particular region, you will reject H naught. Only if your value falls in this particular region, then you will accept H naught, otherwise you will reject H naught. So what is the, let me use highlighter. So this is the acceptance region. Here, this entire thing is the acceptance region. This thing. This particular thing is, entire portion is the acceptance region. I hope you get this thing. And the red shaded region is the rejection region. Acceptance rejection is in terms of the null hypothesis, basically. And here, this side is the acceptance region. This side is the acceptance region. And here, this middle portion is the acceptance region. If you have done statistical inference before, then you will find this very clear. Otherwise, I have tried to make things simpler for you. Again, if you have any questions, you can let me know. And if you find this helpful, please hit the subscribe button and give me a like for this. Okay. Now, next thing, what we will do, we will solve some questions on this. So let us see the first question. Let me write the question. This is question number 1. Question number 1 says, consider the regression equation is as follows. Yi is given to you 0.74347 plus 0.6416 into xi. So this is the estimated regression equation. So alpha cap is this 0.74347 and beta cap is this 0.6416. This is given to you. Now, what are the other things that is given to you is the standard error. Standard error of alpha cap is given to you as this 0.8355. This is given to you, but the standard error of beta cap is not given to you. And the third thing is the t statistic value. T statistic value of alpha cap is not given to you, but the t statistic value for the beta cap is given to you as this 9.5, sorry, 65. 6536. This is the value. Also, n is given to you as 13. That is the sample size. Means the sample size is given to you as 13. Now, what are the things that you need to find out? First thing is find the missing values. Find the missing values. Missing values means this value and this value. These are the two values firstly you have to find. And the second thing is find R square. Now in two variable model, R square, this R square is nothing but equals to the coefficient of determination, right? This we have proved earlier. So basically you have to find out what is small r square, that is equals to capital R square, right? So these are the things that you need to find out. Now, how do you solve this thing? Okay, so let us solve this question. It is given to you that beta cap is 0.6416. See, from this is the beta cap value. And also what is given to you? T statistic value of beta cap. So what you can do from here is that for testing H naught, beta equals to 0, what we know is that t equals to beta cap upon standard error of beta cap. This is what we have done so far. We know this test statistic which under H naught follows Tn minus 2. So that is not required for this question. Now what are the things that you know? You basically know what is the T statistic value. What is the value of T statistic? 9.65, 9.6536. And you know what is beta cap. So this is 0.6416. And you need to find out standard error of beta cap. So standard error of beta cap is simply divide 0.6416 upon 9.6536. So this will come out to be, if you calculate, 0.06646 approximately. So this is one of the missing values, right? See here. So standard error of beta cap, we found out what is the value? 0.06646 approximately. Now the next thing is this T statistic value for alpha cap. Again, we will apply the same thing. We want to test H naught alpha equals to 0, then T alpha cap. Let me call it T beta cap, just to distinguish between this T statistic. This is T statistic for population parameter beta, basically for beta cap here, and this is for alpha. So this will be alpha cap upon standard error of alpha cap. Now you know both these values. What is alpha cap? Alpha cap is this 0.74347. And what is standard error of alpha cap? This is also given to you. 0.8355. So T alpha cap would be simply, if you divide 8898 something, right? This is the approximate value. So our first portion of the question is done. This was 0.8898. So missing values are done. Now the next question is interesting. Find R square or capital R square, whatever you call it, right? So what is the relationship? Now see, from this question, you don't have any other additional information. You don't have any other additional information. You only have the T statistic values, right? You only have the T statistic values for both alpha and beta. Now what we can do, we can derive a relationship between R square and this T statistic and this, sample, sample values, right? Sample data. So let's see how we can derive the relationship. We can derive this in the form of a theorem. Let me derive it for you. The theorem says that R square will be exactly equals to T square plus n minus 2. So this is a thumb rule where this T is corresponding to T of beta cap. Please remember this T is in the form of beta cap. Let us prove this thing, and then we will simply use this right hand side. Then we will simply use this right hand side in order to find out this R square. So let me do that. Proof of this. So to test H naught beta equals to 0, the test statistic is T beta cap. So T beta cap basically. T beta cap, standard error of beta cap. So we start with this T statistic. Now the standard error is also unknown to us. So you can put a cap on this as well. Now individually write what we know. Expand this. What is beta cap? Beta cap is basically, okay, let me go to the next line. What will be T square? Let us start with this. What is T square? T square is simply beta cap square upon standard error of beta cap square. or standard error of beta cap square is variance of beta cap, right? Now, what is beta cap square? Beta cap square is sxy upon sxx whole square. So, square of this, square of this. Into variance of beta cap is sigma cap square by sxx. So, this will be sxx upon sigma cap square. Now, if you simplify, you will get sxy square upon sigma cap square into sxx. Again, sigma cap square is RSS by n minus 2. So what you can write, t square will be sxy square into n minus 2 into sxx into RSS. So simply here simply instead of this, put sigma cap square is RSS by n minus 2. If you put this, you will get this particular thing. Now, what you will do, sxy square n minus 2, this will be sxx, this is syy, and this will be 1 minus r square. This thing I have derived when I did r square equals to r square cube. Refer to r square equals to r square cube to understand this step, right? Now, can you guess what is this? What is this entire thing? Can you identify? I hope you can. This is simply r square. This is simply r square. Then you have n minus 2. And then you have 1 minus r square. So what do you get? T square is this particular thing. Now, 1 minus r square upon r square can be written as n minus 2 upon t square, or 1 minus 1 is this, n minus 2 upon t square, or 1 minus r square is 1 plus n minus 2 upon t square, t square plus n minus 2 upon t square, or what you can write, r square is t square upon t square plus n minus 2, right? And that is how you prove this relationship. So this is a relationship, this is a thumb rule you can remember. So r square, this is how you prove this theorem, that r square can be written in terms of the test statistic value corresponding to slope parameter beta. Now, if you know this relationship, now your r square finding will be very easy. What will be r square? T beta cap square upon t beta cap square plus n minus 2. Now, apply this for our particular case, t beta cap. What is t beta cap value? T beta cap value is this, 9.6536. Put this value here, 6536 whole square, 9.6536 whole square. N is given to you as 13 minus 2. So if you do this, this will come out to be 7.810. So this is how you solve this particular question. So this is the second part of the question, and we have already found out the first part of the question. So both the parts are done. Now let us do a final question and then I'll stop this lecture. Let us see the second question. This question says, consider the model y equals to alpha plus beta x plus u. N is given to you as 10. This is the sample size. Summation xi is given to you as 70. Summation yi is given to you as 80. Summation xi square is given to you as 600. Summation yi square is given to you as 734. Summation xi yi is given to you as 480. Right? These are the data sets that is available to you. Then what you have to do? Test the hypothesis. Test the hypothesis that x and y are negatively correlated. They are negatively correlated. So this is the question. Now x and y are negatively correlated means what? How from this regression equation, how do you, in which terms you can define the negative correlation? This correlation can be defined in terms of beta. See, if beta is negative, then x and y have negative correlation. If this beta is positive, then x and y have positive correlation. I hope you get this from reading this question. So this question is not, straight cut. It has given you this negative correlation thing so that you have to identify reading the question that yes, it means that you have to test the beta population slope parameter, right? Population slope parameter. You have to test this beta and see if it is statistically significant or not, and if it is less than zero or not, right? So that is what we will test. So define the hypothesis first. Let us define the null hypothesis. Null hypothesis is always this versus alternative is beta less than zero, right? This is a one-tail test. This is what I have explained. Negative correlation means beta is less than zero. Now to test H naught, we use the test statistic. We use the test statistic T, which is beta cap upon standard error of beta cap, which under H naught follows Tn minus 2. This is constant. This is so minus beta naught. I am not writing it again because under H naught this beta is 0. So you may not write this, right? Only this much is fine. Okay. Now what you have to do, you have to separately find out this test statistic value. So this test statistic has two components. First component is beta cap and the second component is standard error of beta cap. So we will one by one find this thing and this thing. And if you then divide, you will get the calculated value of t statistic, right? Calculated value of t statistic, and the critical values will be obtained from the a t table, t distribution table that is available in the back pages of your statistic books or econometrics books. So t table, from the t table you have to find out the critical values, and then if you compare you will land up to some inference making. So let us calculate this calculated t statistic then. First let us see what is beta cap. So see, numerator is beta cap. Let us find that out. It is nothing but sxy upon sxx. Again, I am not saying how it came because I have derived it in details in some other video. So please check that out. So this is the beta cap. Now what is sxy? Sxy is simply I from 1 to 10. The sample size is 10, right? Yeah. xi minus x bar, yi minus y1. This is what is sxy means. This is the definition. Then you can simplify in this way. This will be simply if you multiply xi, yi, then you have y bar xi, then you have x bar yi, and then you have x bar y bar. So summation I from 1 to 10 xi, yi, then minus what you can do. This will be y bar will come out. Summation xi, it will be n x bar. N is 10. N x bar minus x bar comes out. This will be 10 y bar. And then it is plus x bar y bar. So summation I from 1 to 10 xi, yi, and then you have minus n x bar y bar. See, 1 x bar y bar will cancel out, so you will be left with only this. Now this values are given to you. Summation xi, yi. Let's get back to the question. Summation xi, yi is 480. So put this 480 here, minus 10 into x bar y bar. So x bar, summation xi is given to you as 70. So x bar is summation xi upon n. So 70 upon 10 is 7. This is 7. And then you have y bar. Y bar is 80 upon 10. That is 8. So this will be 480 minus 560, which will come out to be minus 8. So this is what is your SXY. So this numerator part is done. Now find out what is SXX. Let me do it here only. What will be SXX? Let me make room for me. This is SXX is what? Summation I from 1 to n xi minus x bar whole square. This is what is Sxx. So summation, this can be written as xi square minus n x bar square. Instead of n, you can replace it by 10. N is given to you as 10. So let me write 10 here. So you can basically expand. You can expand this whole square and you will get this thing. I'm not doing it again. You can do it manually. It's very simple. Now what is this summation xi square? This value, summation xi square is 600. This is 600 minus 10 into x bar. X bar we got as 7. So 7 square is 49. So 600 minus 490. So this will come out to be 110. So this SXY value is minus 80 and this value is 110. If you divide, you will get beta cap to be minus 0.727. You can do it on your own. I have calculated it beforehand. So this will what you have. So in order to calculate T statistic, our first beta cap, the numerator part is done. We have calculated what is beta cap. Now find out what is standard error of beta cap. For that, you have to find out variance of beta cap. So what is variance of beta cap? That is basically sigma cap square by SXX. SXX we already have. So find out what is sigma cap square. Sigma cap square is RSS upon n minus 2 for two variable regression model. Now what is RSS? RSS is TSS minus ESS. Right? Now simply calculate what is TSS. TSS is SYY. So this is a question which covers the entire steps that you need for hypothesis testing. So I have chosen such a question which will give you a clarity of how to do the entire thing, right? So let's see yi minus y bar whole square. So summation I from 1 to n yi square minus n y bar square. What is summation yi square? This is 734. 734 minus 10 into 8 square. If you do this, it will come out to be 94. So this is done. Now calculate ESS. How do you calculate ESS? ESS has two formulas, beta cap square into SXX, or you can do beta cap into SXY. These are the two formulas that you can use interchangeably. Here I am using the second formula. Beta cap we have already calculated minus 0.727. And SXY also we have calculated, it was minus 80. So ESS will come out to be how much? 58.16. 58.16, right? Okay. So what is RSS now? RSS is TSS minus ESS. If you subtract, you will get 35.84. Once you have ESS, you can find out what is sigma cap square RSS by n minus 2. So 35.84 upon n is 13. So this will be 11 basically. No, n it's not 13, it's 10. Sorry. N is 10. So this will be 8. And if you calculate, this will come out to be this. Sigma cap square is done. Now what will be standard error of beta cap? It's simply root over of sigma cap square upon SXX. So root over of 4.48 upon SXX we got as 110. 0.2018, right? So everything is done. Now we need to simply find out T calculated value. Calculated T is what? Beta cap upon standard error of beta cap. Beta cap we got as minus 5678 and this is 0.2018. If you compute, this will come out to be minus 3.6. So T calculated is this. T calculated is minus 3.6. Now from the T table in the statistics books, you have to calculate the T critical value. T critical value. T critical value is nothing but T alpha by 2, that is 0.025. Alpha is 0.05, so alpha by 2 is 0.025. N minus 2, N minus 2 is 8, right? This is the critical value that I have told you. This will come out to be minus 1.8. If you see from the statistics books, right? This is the T calculated. So which one is the bigger value and which one is the smaller value? So we see that T calculated is strictly lesser than T critical. T calculated we got as minus 3.6 and T critical is minus 1.8, right? So this is strictly less than that. So if you again draw the diagram for your convenience, so what you see, here you have 1.8, here you have minus 1.8. This is the critical value. See, this is the critical value, 1.8 and minus 1.8, and your calculated value lies somewhere here, minus 3.6 in the rejection region, right? It is in the rejection region. So finally, what we can do, we can take up some decisions. We can write the decision or the conclusion. The conclusion of our test. Conclusion is this. On the basis of the given sample, at 5% level of significance, 5% level of significance, that is alpha is 0.05. We reject our null hypothesis. We reject our null hypothesis and conclude that X and Y are negatively correlated. Right? So this is what we have. We find, or you can write that on the basis of the given sample, we find no reason to accept H naught. We reject H naught or we find no reason to accept H naught, and hence we conclude that X and Y are negatively correlated. So we have enough statistical reasoning. We have enough statistically significant reasoning of saying that yes, X and Y are negatively correlated. Since we see that the calculated value, this is the T calculated value and this is the T critical value. So this is less, right? The calculated value falls in the rejection region and hence we reject H naught. Rejection region means rejection of H naught. We reject H naught. See the how we have defined the null hypothesis. This our null hypothesis was there is no negative relationship between X and Y. Beta is 0. Beta is not significant at all. But alternative states that yes, there is a negative relationship. So we, as we reject H naught, we say that we accept the alternative hypothesis and we conclude that there is enough statistically significant evidence that X and Y are negatively correlated with each other. So by this, we have come to the end of this lecture. I hope you find this lecture useful. I have tried my best to explain this thing in a best possible manner. If you have any questions anywhere, you can let me know. And if you find this video helpful, please do subscribe to this channel, Economist. That will give me immense motivation to do this hard work and make this useful videos for you. And stay tuned for the next lecture where I will be going into the test for alpha, right? So stay tuned for that, and thank you for your time.